Another guy, Ernest Rutherford, looked at radioactivity. The history of all of this stuff is really interesting, but we're just skimming over it. So if you're interested in it, there's a lot more you can learn about it. He studied radioactivity. 3 types of radiation. We're just going to barely touch on this. So alpha particles, alpha rays, are helium atoms that are stripped of their electrons, so helium nuclei. And beta rays are electrons. And then gamma rays are just high energy electromagnetic radiation. Visible light is electromagnetic radiation. Microwaves, ultraviolet light, radio waves. So gamma rays are the same type of energy, just very, very high energy. We have to mention those so that we can talk about Rutherford's experiment, which is pretty cool. So Rutherford, his student, because see, when you get to be a great scientist, you don't actually do any of the experiments. You just have your little minions who do the work for you, and they do all the grunt work, and they tell you about it, and then you explain what it was that happened. So his student fired alpha particles at thin gold foils. So they took this piece of foil made out of gold, very, very thin as they could make it. And they have this little generator, little black box here, that's shooting out alpha particles. So that's the inside part of a helium atom. They're shooting these at this gold foil. The plum pudding model predicted that those alpha particles should just go straight through, because there was really nothing to hit. There's these little tiny electrons, but then this vague charge that's positive, nothing to hit really, so they should go straight through. And a lot of them did, but some of them bounced back. Some of them came back like this. Occasionally you'd get one that came almost straight back. And Rutherford said that this was as surprising as if you took a cannonball, a cannon, fired it at a piece of tissue paper, and it bounced off the tissue paper and hit you in the face. Would that be shocking? That would be shocking. That's how shocking this experiment was. This is not what they expected to happen. Sometimes the best discoveries come when it doesn't work out the way you thought it was going to work out. So what's going on here? Well, here's the plum pudding model. Little electrons and all this just positive charge business. The alpha particles should just go straight through. This led to a new model of the atom in which we have a nucleus which is massive compared to the electrons and very, very dense. And so when one of those alpha particles hit the nucleus, it would bounce back. If it came close, it would glance off and be deflected a little bit. So we could think of shooting airsoft pellets at a volleyball net. Most of them are going to go straight through, right? Airsoft pellets are much smaller than the holes in a volleyball net. A volleyball net, big holes, because the volleyball is big, so you don't need little tiny holes. But what if the airsoft pellet hits exactly the string on the net? It's going to bounce back, right? It can't go through the string. It can only go through the openings. And so that's what they figured out because of this is if these particles are bouncing back, there must be something pretty substantial in there that they're hitting in order to cause them to bounce back. So this led to the idea of a dense nucleus at the center of the atom. So Rutherford proposed a new model, Rutherford's model of the atom. So the negatively charged electrons are distributed around a positively charged nucleus. So here's the nucleus. This is where all the protons are. And the electrons are around this. Now, what the electrons are actually doing is somewhat mysterious. Electrons are very squirrely little critters. And we're not going to talk about them much in this class. You'll get a lot of it in 1A, more than you want. But we don't have to talk about them in this class, so that's kind of nice. So If we think about this, an atom has a diameter of about 1 times 10 to the minus 8 centimeters, and the nucleus has a diameter about 1 times 10 to the minus 13 centimeters. So this is not to scale, this picture here. And just looking at those diameters, that doesn't say much to me, and so I'm sure it doesn't mean a lot to you. So let me give you an analogy. If the nucleus was the size of a green pea, and you set it on the 50-yard line of a football field, the edge of the atom would be at the goal lines. So imagine football field, little green pea sitting on the 50-yard line. And then the whole atom occupies a sphere that would go to the goal lines. And what's in the sphere? Some electrons that are smaller than the nucleus. The atom is mostly empty space. This desk, though, doesn't seem like it's mostly empty space. You could crack your skull on this, right? It's really solid, but it's actually mostly empty space. So let's review these subatomic particles. We kind of mentioned the nucleus showed up in a couple of those pictures, but I haven't told you about it yet. Rutherford could figure out how heavy the nucleus was, and he knew the charge on the protons, and so he figured out there's something else in there that has mass, but it didn't have charge. And so that's how they figured out about the neutrons. So he predicted that it must have some neutral particles as well as the protons. So these neutral particles were called neutrons, okay? We don't try to be tricky in chemistry. We're not trying to give these things crazy names just to mess with you, right? Protons are positive. Neutrons are neutral. Something has to be negative, it's the electrons. So neutrons, they were discovered about 30 years later, but Rutherford predicted that they must exist. The neutron is about the same size as a proton, about the same mass, but it doesn't have a charge. So here we have a nice table from your book. Here's the 3 different subatomic particles, their symbols, their location, their relative charges, their relative masses. This is information that you need to know. Okay, I'm okay with you not remembering 1 over 1836. We're going to call that approximately 0. So if an electron was a grain of rice, a proton would be a baseball. So the grain of rice, its mass is nothing compared to the mass of a baseball, right? It's so small that it's essentially 0. It's almost 2,000 times smaller. And so for a lot of purposes, we just think of the electron as not having mass. Of course it does have mass, but it doesn't matter. It's like if you've got I live in Reedley, and so surrounded by the fruit industry, you got a truck full of oranges, and you go to the truck scale and you weigh, right? Because you have to weigh the truck before you take off on your delivery. And then after you weigh the truck, you throw 1 more orange into the trailer. Are you going to have to go back and weigh that truck again? No. The mass of 1 orange is nothing compared to the mass of the whole loaded truck. It doesn't matter, right? So that's why we can say that electrons don't have mass. But this table, you need to know the information in that table. Table 4.1. Oh, yeah. See, I jump ahead of myself sometimes. So even though it's small in size, the nucleus has 99.9% of the mass. Give you an idea of the density of the nucleus. If you were able to take just nuclei and squish them all together, the size of a period on your page, printed period, it would weigh millions of tons. Little teeny tiny piece of matter. The nucleus is incredibly dense because that's where almost all the mass is, and the rest of it is empty space. So you think of that football field-sized sphere, and all of the mass of it is in the P in the center. That's got to be incredibly dense. I already did the rice thing. Yeah. There's the baseball and the grain of rice, just in case you can't imagine that. Oh yeah, look at this. I already talked about that one too. I do that a lot. So there it's saying a large, the nucleus would be as large as a marble. A green pea, yeah, kind of depends on the size of your atom. But same idea. There's the, oh, see, football stadium. I was talking about the field with the P. So stadium to marble. So this whole stadium, a sphere that big, the nucleus is a marble in the middle. I did this too. If you had a matchbox of nuclei over 2.5 billion tons, it's mind-boggling. Lead's heavy, right? A lead pipe. You know, Mrs. White killed the professor in the library with the lead pipe. Lead has a density of 11.34 grams per cubic centimeter. The nucleus is on the order of 10 to the 13th to 10 to the 14th grams per cubic centimeter. Written out, it's this number. I like to boggle people's minds sometimes.